Hey, all right, so welcome to week 12. And what I wanted to do first was just redo quiz 4. It was the one on glass bottle washing. A lot of times, well, in fact, Bayern Brewery was featured in the Independent recently. It was the same issue of the Independent where I had an interviewer come to my house to look at my zero waste strategy. But a lot of times people say, well, gosh, doesn't it take a lot of energy to wash a bottle versus make a new bottle? And well, yeah, and I think as we've learned recently, everything takes energy. So the question is which takes more, melting a glass bottle, from virgin silicon, or washing one that comes back to the brewery. So and it looks like I might have made an error. So let's just take a look at the question text again. I've got it up right here. So using the specific heat equation, E equals C sub P M times the difference in temperatures, where E is energy, C sub P is the specific heat capacity of water, T sub H is the high temperature, T sub L is the low temperature. Find the additional embodied energy on a per bottle basis if it takes 200 gallons of water that begins a cycle at 20 C and is heated to 100 C to wash 100 bottles, period. While I've got this open, I did want to review a couple of the things. I wish you could see my hands here on the keys. I'm not Julia Childs with the cooking show with the overhead camera, but I did want to show you just a few tricks for editing in Microsoft Word that I just used. There's one where you put a backslash, and if you type \degree, it'll give you that degree symbol, kind of handy. There's another one. These guys, the subscripts, you'll notice the subscript H for high temp. I do that by hitting Control-Shift+. So you can think, or sorry, Control equals, yeah. Control equals will give you the subscript, Control-Shift+ will give you the superscript. So just think of plus as being above, and well, the equal sign is on the same button as the plus, so that's below. Another subtle thing that I recommend you do, especially as you're doing your write-ups for your 15 hours of service this semester, please do italicize your variables. And it's also conventional to not italicize the subscripts. Do italicize the variables themselves, but don't italicize the subscripts. Sometimes the italicized subscripts just get harder to read. So, okay. So now we've got the question laid out. I am going to show you how to solve this using Microsoft Excel. And I've already solved it here. So this is a little bit like a cooking show where, the casserole's already been made. I just want to pop it out here at the end. You can do the same thing in Excel. If I just highlight this one letter, and if I do a Control-1, unfortunately there's not a speed key that I know of, but I can subscript the H there. I'm a high temp. I can also subscript by doing Control-1. What I'm doing there is hitting Control-1. I'll subscript that for the change in temperature. This guy right here is I'm going to turn that into a Greek syllable. The easiest way I know of is to go up here and just type in symbol, and it turns into a delta. And then I just want to get this guy all kind of tidy and looking good. If you're an energy technology student, you will eventually take Al Fraser's ETEC 214. That's energy storage and distribution, and there's a lot of Excel spreadsheeting in that course. Almost every single homework in that course involves a spreadsheet. So the better you get at that skill, the better off you're going to be, and the more valuable you're going to be to an employer down the road who wants you to be a quantitative person in your job. Okay, now, so what I've got is all of the data from the problem. So I've got the high temp in here at 100 C. I've got the low temp at 20 C. I just entered those in. Sometimes it's handy to color code. These guys. Sometimes you put yellow as input. Use whatever you like, but yellow as input. You can put the a calculated formula as some other color. I'm just going to pick that one. Constants. The specific heat of water is a constant. I'm just going to put that in as a blue. And now this is, as you'll notice, it's in kilojoules per kilogram per Kelvin. Doesn't matter if you're using Kelvin or Celsius in this case, because all we're doing is we're looking at a change in temperature. So 1 degree Celsius is the same as 1 degree Kelvin. They're just shifted by 270, whatever it happens to be. You'll also notice that this is the same specific heat if you were doing joules per gram. We're just using kilojoules per gram here. Same difference. It's like multiplying and dividing by 1,000 at the same time. So it's the same as multiplying by 1. I gave you the volume in gallons. I typed in 3.8 liters per gallon. I encourage everybody to use 3 significant digits if you can get away with it. I only have 2 there, so let's go ahead and fix that. Get that up to 3 sig digs. Liters per gallon. And so looking at this guy, 3.78. Now the question is, should that 8 be turned into a 9, or should this be, should this be 3.78 or 3.79? You only got 3 significant digits. Since the 5, if this were 500, if this were 3.78500, we would call that 3.78 because it's conventional in, well, just the way I learned mathematics and science, is to always round towards the even number. But since this 4-1 is there, this number is larger than 3.78500, and we're going to round it to 3.79. So we go back in here, get the full 3 sig digs in there. So liters per gallon, that is also a constant, so I'm going to make it the same color blue. Volume is an entry, so I'm going to keep that as yellow. You can see now, well, I'll show you a couple of the formulas. I didn't show you this earlier, but the delta T is just D2 minus D3. There it is, 80 degrees. Again, we entered that. The volume we entered, liters per gallon, is also a constant. This volume in liters is just the product of the volume in gallons times the volume times liters per gallon. So we're dealing with 758 liters of water. Now let's go look up the density as well. I put in 1.00. I intentionally used 3 significant digits, but let's go look that up again. Approximately 1. I'm gonna hit the engineering toolbox. If we were being super duper scientific, we would go out and go to NIST, the National Institute of Science and Technology. They'd probably give us way too much information. But let's just take a look here. There's a table. And here we are looking at slugs per cubic foot. If you haven't had too many engineering classes before, you probably have never heard of a slug. But a slug is the imperial unit of mass. It's 32.2 pounds. We don't need to mess around with that. Let's just get down into the SI units. You can see here that that water. As the temperature increases, the density of water decreases. Why is that? Well, you've got your crate, jug, container, whatever, of water sitting here. As heat goes in, the molecules start vibrating faster. As the molecules vibrate faster, they're sort of in many places at once. That's one way to think of vibration. You're here, you're there, well, now you're over here. That causes the material to expand and therefore become less dense. That's the reason why things become less dense at higher temperatures, and thus the curve. Now, we aren't going to go, you might say, well, gosh, as I heat the water, it becomes less dense, and now I've got a different function to deal with. I'm starting at 20. Up here there's some number, I'm sure it's in a table, and I'm topping out at 100. And there's actually a pretty substantial, if in fact we are going to use 3 significant digits, well, you might say this is almost a straight line. Halfway between 20 and 100 is 60. There's 60, so we're looking at 0.984, maybe. Let's just take a look. Yeah, there we go. So let's just use this guy. 983 kilograms per cubic meter. That's the same as grams per liter, because there are 1,000 grams in a kilogram, and there are 1,000 liters in a cubic meter. So I'm just going to use 983. I'm going to copy that straight from the website. I'm going to come back into here. I'll paste it there just so I can remember it and put 0.983 into the box. And I'm going to go back and be extra careful to have 3 significant digits there, because that's what I asked you to use here. Okay, so now we've got the density of water, kilograms per liter, and where's this mass coming from? Well, mass is just volume times density, and I'm going to get that also into 3 sig digs. In this case, there's nothing after the decimal point. Okay. Now the energy, that's what we're after in the first place. And let's see, this was yellow, right? Because we were entering the liter. No, this was calculated. Let's turn that into a calculated. Density was a constant. The mass was calculated. Okay, now we finally here get to use the energy equation that we started with. We've got the temperature in there, specific heat, the volume, converted that to mass. Now we can use our equation. So let's see where that comes from. I'm multiplying delta T times C sub P times the mass. And there it is. So we're looking at 249,166 kilojoules. Let's make sure that's correct. So C sub P was in kilojoules per kilogram. So far, so good. The mass was in kilograms, and the delta T was in Kelvin. So fine. So there we go. Now, if we go back to the question, just so we don't make a mistake at the very end, we're washing 100 bottles. So I've got that, 100. Just divide the two together, and there we go. So 2492 is the, well, it's the 4 significant digit answer using an accuracy of 3 significant digits. So I'm going to go back to Sean Doty's answer, because Sean actually said, hey, Professor Layton, I think I might have got this one right, but you answered it incorrectly. So here it is. Somehow, and I just made a mistake in my own math the first time I posted this. I had it at 608 kilojoules. Sean posted in 2531, which is, let's just put it in here, 2531. And as you can see, there are a lot of different ways that number could change a little bit. The error there equals this minus this divided by that, turn that into a percentage. So he was only off by 1.5%. What I typically do when I post these numerical questions, if you're within 1 or 2%, you get full credit. If you're within 10%, you get 90% credit, et cetera, down the line. So, Sean, I did go back in. I gave you full credit for that, and I'll do the same for everyone else that got it right. So that was my mistake, and I hope nobody stressed too much over it. I can see it took about 40 minutes, and that's pretty reasonable. You know, I think once you kind of get the hang of some of this stuff, you can bang these things out, 5 or 10 minutes apiece. And frankly, this is a very, very valuable skill to have if you do happen to find yourself, working for somewhere like Bayer that pays a lot of attention to their energy consumption. So the numbers themselves, I just kind of made up. I don't know exactly how many gallons they use. I don't know exactly what their washing temperatures are. This is just an exercise to say, hey, this is how you would go about solving this problem. You could then go back and look at the embodied energy in a glass bottle. How much energy does it take to dig the sand down to the ground, heat the thing up, send it through the squisher, send it through the former. Guarantee it's more than 2 megajoules of energy. Guaranteed more than that. So maybe we'll do something like that on a final. But here you can actually put into numbers the question that a lot of people come up. What doesn't it take more energy to wash a bottle than make one? I'm almost certain the answer is no. But we could go in and look at the embodied energy for manufacturing and tell exactly what fraction of energy we're saving. Okay, so that was calculated. This was input, and then this was our final answer. Maybe we just put that in red. You guys have any questions, Brian, Jason? Good? Okay. All right, well, my apologies for... Yeah. And another thing, too, that is a lot of energy, though. It really is. And again, it could be they use 200 gallons to wash 1,000 bottles or 10,000 bottles, in which case, you could throw that in. Gosh, like 10,000 bottles. And that 100 I picked because it's boiling water. The water's boiling, and it's going to cook off. 10,000 bottles, obviously, it's less energy per bottle. Let's say it's 1,000. This is still, pretty substantial. I always like to put this in the human power terms and just remember that 10 megajoules is what a human consumes per day. So this means if you were putting all of your energy into bottle washing and it was just you riding a bicycle or rubbing on the bottle a whole bunch, you can only wash 4 bottles per day because you only got 10 megajoules per day. But it's probably not quite that severe there. Okay, so I hope that makes sense, and we can move on from quiz 4. Also I had a few other students saying there were maybe an essay or two question I hadn't gotten to. If that's the case, let me know. I'm going to catch up on all the grading over Thanksgiving break, so you'll know where you stand. I also had another conversation with a student who's distance only and keeping up with the class as best she can, and she was a little worried about her grade and whatnot. I'll put it out there right now. This is the first semester that I'm offering this course, so in a lot of ways, you get to see me work through some of the issues of a startup class. I'm making these questions up from my own using local relevant scenarios, and so really the burden is on me to serve you, the students. So as long as I can see you guys in there trying, participating, I wouldn't stress about your grade a whole heck of a lot in the course. I just want to see participation and that you're trying and actually learning the techniques, and that's going to be sufficient in my mind for a reasonable grade at the end of the semester. Okay, so thanks, and I'll pause there. We'll get on with the rest of the lecture.